Welcome to the next session here now. Our first speaker of this session is Roussanka, with a talk on let terms and where terms of type theory.
Thank you very much. So, thank you for giving me this opportunity to talk about a new theory, which is already for several years I'm trying to develop it. But this type theory of recursion itself is by Yanis Mouskovakis of UCLA. And here is the full story of this theory, by the theory itself. And then I'll show relations with other systems. So this is simple type theory. And it has syntax, so logic language and formal languages. And then this syntax has two layers of semantics. The denotational semantics is standard, as we know it in the formal languages of logic and in type theory. It is following the by structural induction on the term formation. The new thing is the algorithmic semantics. So there is this system has special syntactical tools to represent algorithms formally, recursive algorithms, how the denotations of the terms are computed. So this algorithmic semantics is provided by a special system of reduction calculus. So there is a the minimum number of rules are 10, actually. I counted them here 10, but actually they are 13 originally by Mouskovakis. 13 are by Mouskovakis. Here I wrote 10 because I ignored the congruence. There are 3 congruous relations. So this plus 3 are completely new by me, plus some more. And this reduction calculus, so this system of rules, this is the system that reduces every term in this type theory to its canonical form. So just informally to say that the rules are such that this is not the standard reduction normal forms in Lambda-Calculus. It's completely different. So the other system, the traditional ones, are available for the denotational semantics. These canonical forms are completely different, and they are opposite to the standard for the denotational semantics. I'll explain why. So actually, this reduction calculus is not by me. It is this system, the entire system, syntax semantics, is by Yanis Mouskovakis. So Yanis Mouskovakis, to say that he is probably the best still alive among us, reliable, contributing mathematician, mathematical logician with expertise in set theory. So he is famous with the textbooks that are used, the small version, but with the big set theory, descriptive set theory, and recursion theory. And that is why he came up with this system. So each of these canonical forms, after you take a meaningful term, because there are some terms that have semantics, denotations, but they do not have algorithmic meanings. I'll show which are they. So it takes each algorithmically meaningful term and reduces it to canonical form. And the canonical form is the iterative program for computing the recursive program. So now I shall start with the syntax. So the syntax is simply typed. The type system is not new. It is introduced by Gallin types in 75. The only new thing is this, oh, excuse me. So I'm a little bit clumsy here. This S, this type S is the special thing of Gallin types. So the abbreviations are very good explanation of what is the role of this S-type. This S-type provides expressions inside of the formal language for the informally said about the model, the semantical model, but inside of the syntax. It's for states, the states of the memory in the machine, the states when a programmer writes a program, this program is in some environment of the system, data system, etc. So this is very magical thing. Even we have truth values, we are attuned to think about them as eternal. We evaluate formulas in models. Here we evaluate them with respect to states. So inside of the formal language, there are expressions that can represent the denotation. The denotation is from state S to truth value. So these are state-dependent truth values. So now the vocabulary, there are constants for each type, typically. So the magenta here, the rows, is what I introduced by myself in a special way. Now with the syntax, I'll show how. And the quantifiers, I also introduced them. Here I didn't list them, but because they're not constant, the logical quantifiers. And now the other magical thing that has very big significance for the difference between the let expressions and way expressions are the division. All variables are divided into two kinds for each type. So for each type, this formal system has two kinds of variables. Pure variables are those that we know for quantification, lambda abstraction, assignments in the papers, etc., etc. So here, the recursion variables, they separate the assignments. They're special variables that model the variables in the memory of the computers. So these recursion variables, they represent memory slots for saving information into them. So information is computed and saved into those locations. So typically, including myself, we have been putting together this bunch of variables. So splitting them is the magic that does a lot of work together, of course, with the syntax. So now this is the entire syntactical machinery of the term structure from A to F, 5A to 5F is the syntax of the... So 5A is the typical lambda calculus. 5B is the magical tool by Muscovakis. I did it in semantics, in semantical structures, but not in formal languages. So 5B and 5F, I put them together in mathematical structures for semantics, not in formal language. So Muscovakis helped me here by this special system. And in fact, it's not help to me. It is a formalizing the role of the part of the jobs of the compilers. So 5B, take a look. This is a program inside of the curly braces. These are visually like let expressions, but they're not. I'll show you. There is a proof already. I have proved it. These are more powerful. It's a development of the let expression. So the intuition here is such: compute recursively A1 to AN, and each one, the results save into special memory slots. And then reuse them as many times as you want in computing the major term A0. So this entire 5B is one term where this word has been used instead of let expressions, but here it has different. So I keep let, the word let, for the let expressions. So now, the logical operators, conjunction, disjunction, implication, negation, I introduce them in a special way. So they are special constants having their own interpretations. So they have their own types. So this is called categorical constants, categorically introduced. The other way that we know in the meta language, the interpretation is syncagrammatically. So the quantifiers, So in the paper that Moskowakis introduced this system, he doesn't use them. He uses them informally, both the logical operators and the quantifiers in a meta language. So here I introduced them in the language. Later on, I'll mention why they exist already, these quantifiers. They exist as a higher order generalized quantifiers by special constants. Here I introduce them as pure quantifiers, and there is a relation between them. So this is actually the system from 5a to 5f. This is a system for full recursion. So it's a formal language for recursion. Recursion theory is not a formal language typically. Recursion theory is a mathematical structure of spaces of functions. They can be typed, but those are purely semantical objects. This is a formal language that models recursion theory, represents it formally with formal language. 5f, I introduced it. In the previous talk, in the invited talk, I heard descriptors. I think mu descriptors. So at least for me, how I got it, this such that the 5f term, this is again one single term, and informally it says the value of this term is the value, the denotation of A0, provided that these terms, C1 to Cm, they are of type, the types of the truth values, provided that they are true, all of them. So this is not if then, it's different. I don't say if this is true, then A0. This is a restriction. And it corresponds to, so it is needed, I added there, for the partial functions. So this corresponds from recursion theory to the mu operator. The mu operator, intuitively it says, the list number n such that C1 to Cn. So there you get partiality, partial functions, because the list such number may exist, but if the numbers are ordered, you cannot reach to them because the algorithm will stop and loop on something that's not defined. So this corresponds to the mu operator, but it's generalized. So the other magical thing that Moskowakis introduced, in programming languages, you know that you can loop. You can, one single row of prologue, and you can get a looping program never ending. So the acyclicity constraint provides condition, restriction, how to restrict those recursion term 5b so that we guarantee that those computations always end after finite number of steps. And the intuition is such, if pj occurs in if pj occurs in AI, this means that the denotation of AI may depend on the value that has been computed and stored into pj. So if you find at least one function, ranking function, from these memory slots, P1 to Pn, such that this is provided, the rank of PA is larger than the rank of all the free memories there, in which you are free to save information, then it is guaranteed to stop. So this is a very important restriction of the entire recursive machinery for ending programs. Of course, it's a different story to criteria how you find, because there are many, exponentially many ranking functions, so you have to find at least one, the right one. So here, I'll jump over this, the such that, the restrictor term. Informally, it should be the same as A0, as sigma 0. But because here we are in a type system that has types for state dependency, if there is at least one type, tau1 to tau n, at least one truth value that is state dependent, then sigma 0 has to be lifted to state dependency. This is the intuition of this 8 rules for sigma 0. This is the intuitive. You can puzzle on it. Maybe I made a mistake. So now there is another distinction. Explicit terms are those terms that do not have this where recursion operator in them. But here is a trick. A term can be such that it doesn't have this where constant in it, recursion operators, but the regression calculus will reduce it to the canonical form, and the canonical form may have where. The canonical form is by default a recursive term. Then it's Lambda-Calculus term if it's explicit and there are no recursion variables free in it. So then those terms that do not have any algorithmic meanings are 9. Very simple. Very simple application terms. P is a memory. It applied to pure variables, or it is a lambda abstraction of a such term. So here, why there is no algorithm? Because these are so simple, you get their denotation with no calculations. Directly, yes, directly from the variable assignments and from the memory for P. And then you divide them into kinds. So now, Dana Scott is who introduced the let expressions. And here in my paper that I refer to it, in a recent paper, I provide mathematical proof that actually let expressions are denotationally equivalent to the where expressions, but they are not algorithmically equivalent. So here is why. This is the page, and do I have time to say quickly, at least intuitively? So here 12a is the recursion operator term. So if we want, the characteristic property of the let expressions is 30a, 13a, 30b. B is the characteristic property, the characteristic term of the let expressions. So they're equivalent. So here I cannot directly provide such lambda term over 12a over a for the P1. I cannot lambda abstract over P1 to Pn because those variables are not allowed to be bound by lambda. They're bound only by assignments. So I have to convert them, I have to translate them into pure variables in order to provide such characteristic property. And I provide it by 13c. So in 13a, each one of D1 is not directly A, not directly Di, but it is AI in which those P1 to Pn are substituted with x1 corresponding fresh new pure variables, and then I can abstract. And then if I manage then, so this expression 13a, 13b, if where expressions were equivalent algorithmically to 12a, they should, so 12a and 13b, they have to be algorithmically equivalent. And there is a criteria for algorithmic equivalence, which means that their canonical forms, they have to be isomorphic, so to say. And they're not. So here, after some massages, so this is A prime after this replacement. For the case n equal to 1, the previous one. Here is for n equal to 1. And here I start using the reduction calculus. And this is the canonical form in 17b. 17b is 2 rows. So it is absolutely not equivalent to A. So that's why they are not algorithmically equivalent. So this is the proof. The proof itself is very long. So here I provided a small part of it. So this is it. And the question, do I have time to just put, because the question that Scott put to me, he evaluated very nicely. I was very afraid what he will say for that way I'm more general than the let expression. So he melted down my heart very positively. So I was almost crying in front of my computer. And then he said, I still have a question. It looks to here the denotational semantics. is I'm using just sets, and he's right. So how do we generalize this? I saw all of the papers up to now candidates. I myself did it by dependent type theory of recursion, and situated information. Those states S are full-fledged terms with all sorts of information that you need. This is very important for natural languages, for compilers. In programming languages, you declare variables, etc., etc. So it is important. But here I saw all sorts of new categories, and so this is my story here that I wanted. I hope I gave you some flavor of it.
Thank you very much. Are there any questions?
Yes. See if I can answer right away.
So I'm unfamiliar with the work you're working on, but the point of these where expressions is to somehow give the user control of the evaluation strategy or sharing or something, or what is the algorithmic
Shall I go
point?
to some of the recursion? Do you want me to go?
Or maybe provide a brief intuitive idea of what's the
idea here?
Yeah.
Yes, the idea is, I know what was my idea, but the idea is how this. Actually, there is a simple example that explains the idea. In programming, in first courses in programming, you tell the students, if you have the constant pi, don't use it repeatedly in the program. Because there is an algorithm, pi is a constant, but it is a special constant as many other constants. It's a special, there is algorithm to compute the value. It depends on the rounding, how many digits and all sorts of things. It is a very complicated algorithm, and you don't use pi repeatedly in your program, because each time when you refer to it, it will be recomputed. Better compute it in A1. A1 is pi, compute it and put it in the memory P1, and use it. This is the major. The second motivation, second idea is recursive programs like this. If we skip 5b, so the lambda terms, the applications, they have subterm nested recursively, right? Just by the formation structure of the, and to evaluate it, it has each time when you evaluate it, it's a recursion. For evaluate a term, you have to evaluate the subterms. So you have to stop the program there and evaluate the subterms and book the place where you stopped it, and then you continue in this way, subterms, and then when you compute everything, you have to backtrack. This is the nightmare, exponential nightmare of the recursive programs. This is another thing that when you teach programming, you tell the students, write iterative programs. Don't write recursive programs. When you become a professional programmer, you don't need to do that. Compiler. This is actually formalization. Compiler converts your program into this. Because I explained that to Muscovaki somehow by an email, he immediately hired a PhD student, and this PhD student, in the untyped system, he proved that actually this operator, the reduction, the iterative program, they're also undecidable, and pretty much the same story like not only the iterative, but pretty much the same story as recursive programs. But still, for certain classes of programs, the iterative ones, they don't have this backtracking, exponential backtracking. This is the magical. So that PhD was evaluated by Sheila Greybach. Sheila Greybach normal forms in formal languages. Doesn't this remind you for a rewriting rule? A0, you get it by putting together A1 to AN. So a Greybach normal form is reducing those. So these are at least 3.
Are there any other questions? We have time for a short question. If not, then thanks again.
Thank you very much for listening to me.